Welcome back. Today we're going to continue what we started in the last video with combined loading. Today we're going to just focus on two-dimensional problems. Jump right in with an example. This looks like it's made up of a beam that's pinned to the wall at F and pinned to another support member, DE, and the loading on it is a downward distributed load on member DF. Member DF has a cross section that we're going to look at critical points at the top, at the transition between the two parts of the T and the bottom of that cross section. This is the cross section that's specifically related to this beam. And it might be a little while since you've done statics. Do you recognize that member DE is a two-force member, which means all it can do is apply tension or compression along this axis that's lined up with it. So we can jump straight to drawing a free body diagram of member DF, and we will then find out what the force in this two-force member is that's probably pushing up to hold the beam up. Also, what are the reaction forces out here at point F? And where we actually took that cross section was right here, 5 feet away from point F. So we are just going to zoom in right here on the beam. The cross section is a T shape, and we're going to look at these three locations to find the total stress state. First, draw that free body diagram of the beam that we're interested in. There is the beam. Acting on it at point F, we'll have a force in the X possibly, a force in the Y direction, and I think that two-force member is going to be supporting by pushing up on the end of the beam, so I'll just guess that it's going to act in that direction. Just call that the force in member DE. The orientation of it will match the orientation of the member. I've got 12 feet on this side, 16 feet on that side. If you made that into a right triangle, you'd find that the hypotenuse is 20 feet. So you can call that a 12, 16, 20 triangle if you want, or you can use a similar triangle. It's also a 3, 4, 5 triangle. And then we have, acting on the beam, a distributed load that I will replace with an equivalent load whose magnitude will be 1.8 kips per foot times the length it acts over, which is a total of 16 feet. That comes out to be 28.8 kips that acts downward right at the middle of that rectangle. We have that free body diagram. Let's write our equilibrium equations as our second step to solve for those unknown reactions. If I first sum moments about point F, my applied distributed load will cause a clockwise moment. So that would go in as minus 28.8 kips. Its distance away would be half of 16 or 8 feet. And then if I split up my force in DE into a horizontal component, the horizontal component is lined right up with point F and won't cause a moment. So only the vertical component will cause a moment. Since it acts upwards, it would cause a counterclockwise moment. So I'm going to add the vertical component of FDE. That would be 16 over 20 times FDE. There's the force. And now for some reason, when students are doing these kind of moments, because they've already multiplied FDE by something, they sometimes forget the distance, but this is just the component of the force. Still need to multiply it by how far away from point F it is, which should be the whole 16 feet. Those two have to sum to 0, so we solve and find that the force in member DE is 24 kips. Now we can sum forces in the X and the Y, solve for the other two unknown forces. In the X direction, I have Fx to the right plus the horizontal component of FDE. That has to equal 0. Fx comes out to be minus 19.2 kips, meaning I drew it in the wrong direction. So it's actually 19.2 kips to the left. I sum forces in the Y direction. I'll have Fy minus 28.8 kips from the distributed load, plus that vertical component, 16/20ths of FDE, all has to sum to 0, and we get that the Y component of the force at point F is positive 14.4 kips. So I found all of the forces that act on that beam. Remember what we're looking for? We're trying to find stress state. To find stress, you always need internal loads. And what I just found were all the forces that are applied externally to this beam. If I want to find the stress state right here, I have to cut it open right here and keep either everything to the left of the cut or everything to the right of the cut. I do another free body diagram where we've cut at that purple line. What does my free body diagram look like? It's just a shorter beam section. There is my cut. We have our reaction forces. We figured out Fx is actually a leftward 19.2 kip force. We found out that Fy is an upward 14.4 kip force. Now we have our distributed load. We only want to use the part of the distributed load that acts on this first little part. This is a really common mistake students make with internal loads. They want to say, oh, the distributed load acts over here. We don't need to put it on this little diagram, and that's completely wrong. When we cut it, we've also kept just this part of the distributed load. So we're going to have just a little bit of the distributed load that acts on this cut. So let's replace that with an equivalent force. The distributed load had a magnitude of 1.8 kips per foot, and we are only keeping the part on the first 5 feet. So this total force is going to be exactly 9 kips. Then at my cut, I need to find the internal loads. In 2 dimensions, the internal loads will be a normal force, a shear force, and a bending moment. Those are the 3 things we're trying to solve for my internal forces. So next, again, we're going to use equilibrium. If I sum forces in the x direction, I've got normal force to the right minus 19.2 kips to the left equals 0. So my normal force is 19.2 kips. If you want to remind yourself, that's actually a tensile force because I drew it assuming that the rest of the beam that I'm not drawing is tugging and pulling to the right. So this would be tension. Let's sum forces in the y direction. I've got upward 14.4 kips, downward 9 kips, and also I drew it downward on my diagram because that's our standard sign convention for shear and moments. V downward, all of that equals 0, and solving, V comes out to be 5.4 kips. It's a positive, which means I drew it in the right direction on my diagram, so it does in fact act downward. And finally, let's sum moments. If I sum moments about the cut, has to be 0. M is in a counterclockwise direction. The 9 kips, which is half of 5 or 2.5 feet away, will also cause a counterclockwise moment, but the 14.4 kips will cause a clockwise moment. So we put that in as a negative. That is 5 feet away. We set it equal to 0 and solve for our bending moment. It comes out to be 49.5 kip feet, and it came out as a positive, which means it does in fact on that cut surface act in a counterclockwise sense. We're making great progress. We did 2 free body diagrams. The free body diagram of the whole beam allowed us to find these external reaction forces. The free body diagram cut open at the purple line allowed us to find all of the internal forces. So our next step, we're going to take all of these forces and we need to find the stress that they each cause. I find that's most helpful if I first find all of my section properties. What are we going to need? Normal force, we're going to be dividing by an area. So we're going to need the area of the shape. What is our shape? Let's go grab the shape. It's a T shape right here. Let's copy down that cross section. 7 inches across here, 1.5 inches right there, 1 inch right there, and 6 inches right there. We've just said for normal stress, we're going to need the area. So let's first find the area. That's pretty easy. 7 inches times 1.5 inches plus 6 inches times 1 inch. That is 16.5 inches squared. We are also going to need for our bending stress, do you remember bending stress is my over I. So I need the moment of inertia of this cross section about its centroidal axis, and I don't know where its centroidal axis is. So the next thing I like to find is the centroid, y bar. To do that, I like to break this up into a couple of different colored shapes. Make that one blue, make that one green. I guess I could have used those same colors when I found the area. So if you want, make those ones blue, and we can make those ones green. So y bar relative to my reference line is going to be the sum of the y tildes times the areas over the total area, which we already found the area. That's 16.5 inches squared. Definitely don't calculate it again if you've already found it. For our 2 rectangles, I need the location of their centroids relative to the reference line. So this first one is going to be right there. I will multiply that distance 0.75 inches times the area, 7 times 1.5. And then I need to add to it for the green rectangle. Where is its centroid going to be? It's right here in the middle of the rectangle. To get all the way to my reference line, I've got to go 3 inches plus another 1.5. 4.5 inches for the y tilde, and the area is 6 by 1. And we get a number for y bar. It comes out to be 2.1136 inches. Reminding ourselves that is from the top. I mentioned that I also need the moment of inertia of that cross-section about its centroidal axis. So let's start with the blue rectangle. Moment of inertia for a rectangle about its own centroid is 1/12 bh cubed. Base would be 7 inches. Height would be 1.5 inches, which gets cubed. Add to it the area, 7 inches times 1.5 inches, times the distance between the centroid of the blue shape and the entire centroid, which I never really drew on here, is going to be somewhere around there is my x prime axis. And that's the axis we're finding the centroid about, so I need to plug in here 2.1136 inches minus 0.75 inches, and I square that. Then we add for the green, the rectangle, so it's again 1/12, the base is 1 inch, the height is 6 inches, which gets cubed. That's the moment of inertia about its own centroid. Then we need to add to it area, 1 inch times 6 inches, and distance squared, which would be the distance between the centroid of the green rectangle, 4.5 inches down, and 2.1136, which is the centroid of the whole shape. That gets squared, and that all together comes out to be 73.662 inches to the fourth. Let me circle what we found so far. We found the total area. We found the location of the centroid. We have found the moment of inertia. We need to find Q. They're asking us to find the shear stress at 3 locations, point A, point C, and point B. Here's our cross section. They want us to find the stress up here at point A on the top, down here at point B on the bottom, and at point C, right at the transition between the two shapes. If we go to calculate Q for point A, do you know what we get? Remember how we do Q? Our shear force is acting downward on the cross section, so you draw a line through point A, and you either shade all the area above it, which has an area of 0, or you shade everything below it, which has an area of the whole thing, 16.5 square inches. Then you multiply that area. I prefer to take the one that's already 0, but let's say you took the entire area down here. You multiply it by, guess what? The distance between the centroid of your shaded area, whose centroid is right there, and the centroid of the whole shape, which is right there. So either you think of it as you keep the area above, which is 0, or the area below, and then your y bar prime is 0. So Q at A is 0. Guess what Q at B is? Also 0, because if you take a line right here and you shade all the area below it, there is no area below it, so QB is also 0. So as a reminder that shear stress varies parabolically with no stress at the extreme edges and max stress at the centroid. So what about C? That's the only one we have to calculate. The equation is y bar prime A prime. Let's shade in our area. So we're going to draw a line through C, shade everything either above or below. Y bar prime is the distance between the centroid of that shape and the centroid of the whole shape. Oh, we already kind of did that math up above. That's going to be this thing right here. 2.1136 is the centroid of the whole shape. The centroid of A prime is at 0.75 inches. So 2.1136 inches minus 0.75 inches is y bar prime. And then what's A prime is just the area of the top rectangle, which was 7 inches times 1.5 inches. That comes out to be 14.3178 inches cubed. At this point, we need to find the stresses at all of these points and find their stress state. I think it's a little easier if we just take it at one point at a time. So let's do point A. At point A, let's do the easy one. Tau A, well, that's VQ at A over IT. Q at A is 0, so there is no shear stress at point A. What about the normal stress at point A? Well, normal stress is going to be a combination of normal force over area and My over I. And I like to put plus or minuses here, and I'll go figure out, are they going to be positive or negative? Let's look at our normal force. Our normal force was a tensile force. So that's going to give us a tensile stress, which we're going to call positive. So we'll plug in 19.2 kips. If you want to write down the plus to make sure you really did look at it to figure out what the sign is, that's a great idea as well. And the area, we found that right up here. The area is 16.5 square inches. And then we need our My over I. Well, our moment was 49.5 kip feet. Let's convert feet to inches. I've got 12 inches in 1 foot, so those feet will cancel. And what do we multiply M by? M gets multiplied by Y. Y is the distance between the centroid and the point where we're finding the stress. So if the centroid is right here, finding the stress at the top, it would simply be the whole 2.1136 because we measured our centroid from the top. So our y distance is going to be 2.1136 inches. Then we put our moment of inertia on the bottom. That was 73.662 inches to the fourth. Now, is that going to be positive or negative? I will have to go and look and see. My bending moment acted in this direction, and I got a positive sign, which means it does in fact act counterclockwise, which on this face means you're pulling at the bottom and pushing at the top. So we're going to have compression at the top. Compression is negative. They're going to subtract from each other, and we get that the normal stress at A is minus 15.9 kips per square inch, or KSI. We had kips per square inch here. We'll end up with kips times inches squared over inches to the fourth, which is also kips per square inch. Comes out negative because the bending stress is bigger than the stress from the axial load. And what we often like to do is draw a little sketch. So here's point A. What it represents is not on this picture. It represents going all the way back up to the beam. Point A is right here at the top, and we're taking a little tiny chunk of material right at the very top, and we're trying to show graphically how is the stress acting on it. So the point that the face that matters is the right edge. On that right edge, we have no shear stress, and we have a compressive normal stress. So we draw it on here like that, and we always put the other one on so it's in equilibrium. And we have the stress state is 15.9 KSI in compression, which looks like that picture. Let's do point B. Shear stress at B is V times Q at B over IT, which will be 0. Normal stress at B is probably not 0. It's going to be plus or minus N over A plus or minus MY over I. N over A, do you remember how this behaves over a cross section? It's absolutely the same everywhere in the cross section. So we can just copy down 19.2 kips divided by 16.5 inches squared. The bending, same bending moment, 49.5 kip feet. Convert 12 inches in 1 foot to cancel the feet. Moment of inertia is the same, 73.662 inches to the fourth. What's going to be different is how far away we are. Point B is down here, centroid is there. I need to find that distance. The whole thing was 1.5 plus 6, so 7.5 inches. The centroid is this far from the top. What I want to do is take 7.5 minus 2.1136, and that'll give me the distance between the centroid and the bottom. 7.5 inches minus 2.1136 inches. Will it be tension or compression? If you're at the top, it's in compression. At the bottom, it will be in tension. You can also go back and look at your bending moment again. The bending moment acted this way. So since the arrowhead was squeezing in at the top in compression, it would be coming out at the bottom in tension. We run through those numbers, we're going to get a positive this time. So the normal stress at B is going to be plus 44.6 KSI. So my picture for point B would look like this. Again, no shear stress, but we will have normal stress, and this time it's tension. 44.6 KSI is what the stress state looks at point B. Let's do point C. This is the hardest one because it does have shear stress. At point C, let's first do the shear stress at C. Well, it's going to be V times Q at C over I times the thickness. I don't know if it made it really clear in the original picture where point C is. It's right at the junction between the bottom and the top of the T-shape where the thickness jumps from little 1 inch to giant 7 inches. I am going to go ahead and find the stress in the thinner section because it's so much of a bigger stress. So let's find it in the thinner section where thickness is going to be 1 inch. Plugging all the numbers into our equation, our shear force was 5.4 kips. We also calculated Q at point C. That's right here, 14.3178 inches cubed. Moment of inertia is the same as we were using before, 73.662 inches to the fourth. And the thickness was that thinner 1 inch section. It comes out to kind of a small number, 1.049. The units will be kips per square inch, or KSI. And I like to remind myself that this was caused by a shear force that was acting downward on my cut face. That'll be helpful when we draw our picture at the end. Next, let's do normal stress at C. It's going to be plus or minus N over A plus or minus MY over I. The normal force piece is exactly the same. Doesn't matter where on the cross section. It's always going to be the 19.2 kips divided by the 16.5 inches squared. And now the bending moment piece, the moment's the same, 49.5 kip feet. Convert 12 inches in 1 foot. I'll put in the y distance in just a second, and we're going to divide by moment of inertia, 73.662 inches to the fourth. Need to figure out if it's tension or compression. I need to figure out that y value. Point C is right up there at the transition between the blue and the green areas. So I need to know how far is it from the centroid of the shape. Well, point C is 1.5 inches from the top. The centroid is 2.1136 from the top. Subtract those and you'll get the right distance. 2.1136 inches minus 1.5 inches. For our distance, is it tension or compression? Is point C above or below the centroid? Point C is above the centroid, and we have a problem where if we're above the centroid, we are in compression. So this will be negative because we are in compression. And when we combine those, we get this normal stress at C is minus 3.78 KSI. Now let's draw the little picture for point C. This one is much more interesting than the others. Let's first do that compressive stress. Again, we were finding it based on this being our cut face. So it's compression on that face means it points in that way. And then we need an equal and opposite one on the other side. So there is our 3.78 KSI. The negative means compression. And now our shear stress. Here's where this little picture helps me so much. I knew when I originally saw for shear force, it acted downward. So my shear stress on the cut face will also act downward. So I draw right here 1.049 KSI. If you want to make that 1.05 so that it's 3 significant figures, that would probably be even better. We can't leave it like that. That would not be an equilibrium. So this downward arrow on that side needs to have an upward arrow on the opposite. And then can you see that this little square would start rotating because these two are unbalanced as a moment? So we also need to draw another pair of arrows like that so that the heads point toward each other. What we used our original diagram for was to figure out the direction of the shear stress on the side that matches up with our cut face. Once you start with that, you just add arrows that are head to head and tail to tail. And that is what the stress state would look like at point C. What I want to point out to you about this is this was a great problem. However, look how much work it took for us to find these stresses at one spot in the beam and only 3 spots on their cross sections. So what if I wanted to find the stresses right here? I would need to repeat most of this work. The section properties would stay the same. I could still use these, but from here on down, I would need to redo pretty much everything. That is a lot of work to keep hunting along on here to try to find where is the stress maximum, when is this going to fail. So my second example is kind of designed to help us see how we can be a little bit more efficient with choosing where we're going to calculate things. So what we have here is a simple beam fixed on one end with a point load on the other end. The section's a little bit complicated. It's this kind of channel section made of 3 built up rectangles, but they ask us to find this time the max normal stress and the max shear stress anywhere in the beam. So instead of telling us to come over here a certain distance and cut it and find the stress there, they want the maximum values. So what's going to help us get maximum values is actually shear force and bending moment diagrams. They will tell us where along the beam is the shear force and the bending moment maximum and how big are they. So let's start, as always, with a free body diagram. We have our applied 2.6 kilonewton force, which acts at that 5, 12, 13 orientation. At the wall, we will have an AY, AX in some direction, and maybe an applied couple MA because it is a clamped support, so it provides all 3 of those reactions. If you want to do equilibrium really quickly, which we do, the downward vertical component of this would be 2.4 kilonewtons, and that has to be exactly balanced out by AY, so AY will be 2.4 kilonewtons. AX will be the horizontal component, which comes out to be 1.0 kilonewtons, because the horizontal component of this force will be 1 when you take the 2.6 and multiply by 5/13. And the moment about point A has to exactly counteract the moment that the vertical component of this force causes about point A. So you take that vertical force, 2.4 kilonewtons, multiply it by how far away it is, 3 meters, and you get that MA is acting in the correct direction on my drawing. It is 7.2 kilonewton meters in magnitude. So I just kind of did free body diagram and equilibrium. Next, shear force and bending moment diagrams. We didn't do this on the last problem because we were taking a cut and finding the internal loads at a specific location. For this problem, V and M diagrams will help us find the answer. Shear diagram. The first thing that happens shear force wise is we first have a downward force of 2.4 kilonewtons. So we're going to come down here to minus 2.4 kilonewtons. And then look, we have no distributed load. So we have a slope of 0 all the way to the end of the beam, where we have a reaction force that then goes back up 2.4 kilonewtons. So there is our shear force diagram. It does give us the key information that V max is 2.4 kilonewtons in magnitude. So we'll use that to find our max shear stress. Then we need a bending moment diagram. We have no applied couples at the end here, so we're going to start at 0. And then we are going to have a constant slope of minus 2.4. Constant slope means down like that. Slope is minus 2.4. It should end up at 7.2 kilonewton meters down. So we should jump back up to 0 with an applied clockwise moment of 7.2 kilonewton meters. If you wanted to calculate it, you could use the area under here, which is 2.4 times 3. Oh, wait, those are the same numbers we used to get the 7.2 in the first place. So definitely down here, we're going to end up at minus 7.2 kilonewton meters. And max is going to be 7.2 kilonewton meters. And M max is going to act right here at the very, very end of the beam. So we did our free body diagram, we found our reaction forces, we drew shear force and bending moment diagrams to get V max and M max. Now let's go and figure out the max normal stress and the max shear stress. To do that, we're going to need some section properties. Our section looked like a channel. We had a rectangle on the left, a rectangle in the middle, and a rectangle on the right. I decided to make a reference line at the top right here. Let's first find the area. This is 250 millimeters. These are both going to be 15. The orange ones have a height of 200 millimeters, and this little pink one has a width of 20 millimeters. The area of my pink one is going to be 250 millimeters, or 0.25 meters, times 20 millimeters, or 0.02 meters. Then we need to add to that the orange ones, and there are 2 of those. They are each 200 millimeters, or 0.2 meters, times 15 millimeters, or 0.15 meters. Multiplying that out, we get exactly 0.011 meters squared. So we have our area. We also need to find the centroid location, which is why I drew a reference line on there. So y bar is the sum of the y tildes times their area divided by the total area. I know the total area now is 0.011 meters squared. In the top of the fraction, for the pink rectangle, I've got to come down 10 millimeters, 0.01 meters, to get to its centroid right here. And then I also need to multiply it by its area, which was the 0.25 times 0.02. And then we need to add to it 2 of these, whose centroids would be 100 millimeters down from the reference line. 0.1 meters is the y tilde, and the areas would be 0.2 meters times 0.015 meters. And we multiply all of that out and get y bar is 0.05909 meters. I like writing this down in millimeters. It helps me realize, is it a reasonable number? Centroidal axis x prime would be 59.09 millimeters down from the reference line. We're going to need moment of inertia about that centroidal axis. Pink rectangle will have 1/12. The base is 0.25 meters. The height is 0.02 meters, which gets cubed. We add 2 at that area, 0.25 meters, 0.02 meters, times the distance between its centroid and the centroid of the whole shape. So 0.5909 meters minus 0.01 meters. That gets squared. Then we need to add to this 2 times 1/12. Their base is 0.15 meters. Their height is 0.2 meters, which gets cubed. Their area is 0.15 times 0.2, and the distance would be 100 millimeters, 0.1 minus 0.5909 is the distance between the centroid of the orange shape, 100 millimeters down, and the centroid of the whole shape, 59.09 millimeters down. We do all of that math, I get 42.26 times 10 to the minus 6 meters to the fourth. So I have my y bar prime from the top. I have my moment of inertia. It wanted max shear stress. So the only Q I need is going to be Q max. So for Q, let me just draw quickly this shape one more time. Our centroid is right about here. So to find Q, you need to either calculate the Q for the area above the line or the area below. It is frankly easier to do it for the area below, but just for fun, why don't we do the area above so we can practice that handy trick from a couple of classes ago of summing Q's. So let's use that area right there. My distance down here was y bar was 59.09 millimeters down. And let me shade these different colors. Since it only wants the max shear stress, it doesn't want the stress right here or here or here or here. It just wants the max. Max is always going to be at the centroid, so I shaded it right above the centroid. So finding Q max, I can find it as a summation of all of the Q's. Remember, which is a summation of the y bar primes times the a primes. So we'll have a blue one. Its y bar prime would be the distance between its own centroid right here and the centroidal axis of the whole shape. So its y bar prime will be 05909, that's the centroid of the whole shape, minus 01 is 10 millimeters for the centroid of the little blue shape. And then its a prime is its area, 0.25 meters times 0.02 meters. Then I just need to add to it 2 of those green things. Now for the green things, I need the distance between the centroid of the green thing, and here's why I wanted to not use the same color as up here. I don't want the centroid of the whole orange rectangle, which is down below it. I want the centroid of the little green shape, which is going to be right up here. The green shape is 59.09 millimeters long, so its centroid would be exactly half of this distance away. So my y bar prime for these is just going to be 05909 meters divided by 2. And then my area would be 05909 meters times how wide it is, which was 15 millimeters, 015 meters. These are the y bar primes. For this blue rectangle that hasn't been cut at all, it's just the distance between the whole centroid location and the centroid of the blue rectangle is 20 millimeters tall, so its centroid is 10 millimeters down. So you just take 10 millimeters away from this number to get that distance. For the green ones, though, the rectangles are sitting right next to the centroidal axis. The height of these chopped off rectangles is 59 millimeters. So to get the distance between their centroids and the center of the whole shape, you just take the 59.09 and divide it by 2. So we get Q max. It comes out to be 2.978 times 10 to the minus 4th meters cubed. And I have all the section properties I need. So now we can find the max shear stress. Max shear stress will be V max times Q max over moment of inertia times thickness. What was our V max? V max had a magnitude of 2.4 kilonewtons. Q max was 2.978 times 10 to the minus 4th meters cubed. Moment of inertia was 42.26 times 10 to the minus 6th meters to the 4th. And thickness, this is the thickness that we cut through when we drew our line. So thickness is going to be one green plus another green. The green ones were 15 millimeters thick. So I'm going to have 2 times 15 millimeters or 30 millimeters. That would be 0.3 meters for my thickness. And you multiply that all out and you get 563.7 kilonewtons per square meter. And a kilonewton per square meter is a kilopascal. So I'm going to call that 564 kilopascals. You'd also be totally fine to call this 0.564 megapascals. Either number works. That is the biggest shear stress you find anywhere in that beam. Happens at the centroid location. And it's actually the same anywhere you cut the beam because look at our shear diagram. V is the same everywhere along the entire beam. Now we need to find the max normal stress. So remember our equation for normal stress was plus or minus N over A plus or minus My over I. I actually want to go and find the stress at the top and the bottom because I don't know where it's going to be bigger. So if we go to find the stress at the top, And then in just a second, we're going to find the stress at the bottom. We know that N over A doesn't change whether you're at the top or bottom of the beam. So let's plug that one into both of them. Our normal force was the same everywhere. Our normal force is just 1 kilonewton, and it's in tension. Can you see that? The force here and the force there is going to be in tension because this, ultimately, the X component is pulling on the beam. So 1 kilonewton is our N, and it's going to be positive. And what's the area? The area was 0.011 meters squared. Now we need to add in the stress from bending. So I'm going to plug in my bending moment, which has a magnitude of 7.2 kilonewton meters. I need my moment of inertia. Moment of inertia was 42.26 times 10 to the minus 6 meters to the fourth. This stress is the same everywhere on the cross section. The bending stress has its extreme values at the top and bottom. So I just went ahead to find the stress at the top and bottom, because you remember bending stress is 0 when y is equal to 0, and it gets bigger and bigger as you go farther away. The centroid is right here. The top is going to be 59.09 millimeters away. 05909 meters is how far you have to go from the centroid to get to the top of the beam. Now bottom, the whole height of the beam was 200 millimeters. So to get from the centroid to the bottom, it's going to have to be 200 minus 59.09. That's 0.2 meters minus 05909 meters. Now, which is positive and which is negative? It's essential to get the right answer. Well, let's look at which direction the bending moment acts. The bending moment acts that way. What does that mean? You could think of it this way. We're pushing down on this overall, so it's going to curve downward. In order to do that, you're taking a beam that was straight, and you quite literally have to stretch out the top of it and compress in the bottom of it to get that kind of curvature. Alternatively, you could look at your actual reaction moment, because right here at the wall, that reaction moment is the internal bending moment. And can you see how it's pulling and pushing like that? That would be the way you get that kind of couple, is with tension at the top and compression at the bottom. So at the top, we have tension, and these two will add, and at the bottom, we have compression, and these two will subtract. At the top, we end up with 10.08 megapascals, and at the bottom, we end up with minus 24.0 megapascals. So when we're asked for sigma max, we're usually wanting that in an absolute value sense. So that would be 24.0 megapascals at the bottom. And I think it's a little bit interesting that even though these two were the same sign, so they added, it ends up being a smaller magnitude than here where they're subtracting. And it's because this bending stress is much bigger than this stress. And this value is so much bigger than that value because that centroid is shifted toward the top. So you get a much bigger stress when you go the farther distance to get to the bottom of the beam. All right, I think that is enough for today on 2D combined loads. Showed you two different example problems. The first one had us zooming in a very specific location to find the stress at 3 specific points on the beam. The second problem had us just analyzing the beam as a whole and finding where is the shear stress max and how big is it, and where is the bending stress max and how big is it in an absolute sense. Thanks for watching, and we'll see you next time.